Good evening, everybody. And tonight is the third Thursday night for our live member and consultant network meeting from Austin. And this time we are joining Edward co-host with a bunch of other live member group from Lone Star, Dallas, Fort Worth, and Houston, and Denver. So hopefully they'll join in a little bit later. Maybe just talk a little bit about the Austin group. We have about 400 some people, but we had a very good outing in May. We went to the Wildflower Garden for one evening, one morning. Then we for a live member conference in next year in April, April 14 to 16. We'll be in the Hyatt Regency Hotel, just south of the river of Austin. And we're still in a planning mode. So we're looking for speakers, recruiting speakers, and send a program out. So this is a 3-day program. And I'd like to remember, you're welcome to join us. So there'll be a corporate talk about some of the tech product for aging population. We also have a corporate visit in some of the facility in Austin, and so hopefully that'll be a good event. And for people outside the state, probably Austin will be a good place to watch the eclipse on April the 8th. So that's a date that people NASA predicted. And so that's the only announcement I have. And also next month we're going to have a local company, Inspire Semiconductor, talk about the RISC-V product that can support all kind of AI application, different high performance computing type application. So this is a second RISC-V talk that we'll have this year. So those are two announcements I have. One is the live member conference next year. In July, we have a program on RISC-V. And his first, hopefully you can see the third page from Brian. It has all the IO on the first page. So Brian, the floor is yours.
Okay. Well, thank you, everyone. And I'm going to give a discussion today on 5G and 6G. And I know everyone has heard 5G. You probably all have 5G phones. I'm going to try to explain what the big deal is. Like, why in the world is there so much hoopla around 5G? As part of my background, faculty background, I'm a associate professor of electrical and computer engineering in the Department of ECE at the University of Texas at San Antonio, in the Kellery College of Engineering. My undergraduate degree was from Cornell, and my graduate work was at Georgia Tech. When I graduated, I joined industry. So I was with both Motorola and a subsidiary of Motorola that spun off called Freescale, and then joined the University of Texas at San Antonio after a stint in industry. So part of my expertise while I was in industry is in cellular communications. I was in a group that developed mobile handsets for cellular, and I also had the opportunity to be a representative of my company in the standards body referred to as the 3GPP. After joining the University of Texas at San Antonio, I introduced courses on 4G and now 5G. And so I teach courses on 5G, and had an opportunity 3 years ago to be selected as a principal investigator in 5G for the Office of the Undersecretary of Defense, representing two programs at Joint Base San Antonio, one in 5G core security and the other in 5G telemedicine. And then as of the last 4 months, I transitioned to a new role as principal investigator in what's called Future G Advanced Research for OUSD R&E. So I've got a lot of the most recent and contemporary information on 5G, and I just want to, and 6G, and I want to try to share it with you to expose you to what's going on and why it's such a big deal. Okay, so 5G systems, I often tell students when I teach classes on this, can be thought of as a mobile version of the internet. So essentially what's happened is that traditionally, we all, would take our computer, plug in to a, Ethernet cable somewhere, and would connect to the internet over, let's say, Ethernet, which effectively in today's world has become Wi-Fi. So Wi-Fi access points plug into, a computer network, and then we get, signals referred to as Wi-Fi signals, typically on our computers in our offices or at home, or sometimes we still plug in directly through Ethernet. So think of 5G as really taking the capability and the performance of a wired network and allowing that to occur in a wireless space. What you can see in the diagram above is that we've got a core network, an access network, then we have wireless, a wireless channel, and then a mobile device. So think of this system here as representing an abstract version of what we typically consider to be a wireless communication network. In today's terms, this element here is in the cloud is where our apps reside. So we typically have applications, you download it onto your phone, but there's normally a host application running at a server in the cloud for whatever service provider we're connected to. That application interacts with the core network of our wireless provider. And this core network offers communication services that can then be transmitted to a wireless access network for transmission over the air. Okay, so the core network are the services, the wireless network, which we call a radio access network, then takes the information stream, converts it to a symbol stream, and then transmits it over the air, and ultimately ends up at our user equipment or our mobile phone. But the end devices could be phones, watches, computers, vehicles, any entity that is connected to the cellular network. Now, in terms of actual 5G operation, the standards body, which is typically referred to as the 3GPP, Third Generation Partnership Project, decided to define specific capabilities in more depth. And so they defined really 3 capabilities in 5G that tend to be the core capabilities that most groups rely on. One is referred to as ultra low, one is referred to as massive Internet of Things or massive machine type communications. And that supports a ultra high density of devices, up to 1 million devices in a kilometer squared. The second one is enhanced mobile broadband, which supports very high data rates, hundreds of megabits per second typical, peak data rates on the order of gigabit per second, 1 to 2 gigabit per second peak data rates. And then ultra low latency as low as a millisecond. So these are some of the operations that 5G supports. So let's look at 5G in a little bit more detail. So when we look at 5G, there are different ways you can look at it. One is a physical representation. And this is probably the way most people are more comfortable with, is thinking about, connecting physical things together. So in 5G, we have a core network. And remember, I said the core network is where the communication services reside. We can have what's called an edge network, or sometimes you hear the word MEC or MEC is the acronym. That's a multi-access edge computing system. And this system allows us to take kind of a mini application or take an application and put it on a small cluster of computers closer to the edge of the network, with edge being defined as close to the radio access network. And then that communicates with the UE. So if you look at it from a physical connectivity perspective, there only are 4 or 5 elements that you have to think about: the mobile device, the radio access network, an edge application server, a core network, and then the core network actually communicates typically to applications in the cloud, with the core itself also being hostable on the cloud network. Now that's sort of the physical perspective. If we look at it from a different perspective, we can think about it as a virtual network as well. And so when we talk about a virtual network, what we're saying is we have certain operations that we're going to compute or enable, and those operations can be virtualized on virtual machines. So these are not necessarily physical things, but virtual machines that can reside in any physical host server at any location. Other capabilities are something referred to as network slicing. And so what you see here is sort of the expansion of the physical system above now into certain virtual concepts. So we still have a public cloud, we have a core, we have an edge computing system, but now the radio access network here can be what we refer to as disaggregated. It doesn't have to reside in one location. So here, it's looked upon as residing in one location. But we can actually break it up and have different elements reside in different locations. So the radio access network in 5G is decomposable, or we use the term disaggregate, or it can be disaggregated into a radio unit, a distributed unit, and a centralized unit. And so this radio access network can actually reside in multiple locations simultaneously, with each performing a different portion of the communication protocol. There's virtual network infrastructure, physical network infrastructure, and then there are network functions that operate within the core. There's a management system referred to as a management and network orchestration system. And then we have multiple tenants residing on it. So here, think physically, but these physical systems are performing certain communication and application operations, and those operations can be moved around to different locations. And that's how we start getting into the notion of virtual operation. Any questions on that? Okay, so what is the why is there so much of a ruckus, I'll use that word, about 5G? And the key term that you can think about here is convergence, okay? So 5G, in addition to essentially enabling a mobile version of the internet, meaning you can basically go anywhere untethered and have performance similar to wired Ethernet. 5G represents a convergence of cloud computing, wireless communications, and computer networking. Okay, so these three elements essentially formulate the basis for 5G. Now, if you look in this diagram, before, remember I was showing you the computer network that was connected to a core network, and then that was connected to a radio access network, and that communicates with your phone over an air interface. So think of this as, this is your cloud, this is your core, this is your radio access network, and sort of hovering in the control plane above the control, and also what's referred to as the management plane above the communication transmission, are a large set of applications, many of which can be run on standard commodity servers that you can either operate on premise or you can place in the cloud. So what 5G is able to do is it's able to leverage all the existing cloud applications in a very seamless way that can be integrated. So this is one of the huge benefits. If you have an application and it's currently wired, it's very seamless to integrate that in a wireless environment using 5G. And all of these applications run on the same kind of servers, believe it or not, as the functions, as the communication service functions that represent the core network. So if we think about the cloud, one of the trends in cloud computing is to move from what we call virtual machines to a more efficient virtual machine framework referred to as containers. And this is more of an efficiency model. So historically, we took a physical computer, and we would add a hypervisor on it. And rather than having like one operating system, we can have multiple guest operating systems on the same physical resources. And then our applications can run as if they are running on different physical machines, but they're not. They're basically running on virtual machines. And so operating systems like this on virtual machines enabled us to allocate the amount of computing resources that a specific application needs. We can size it, we can scale it much more easily. We can also move the virtual machine image to different cloud data centers and use the resources of a data center to host our virtual machines. Now, the trend today is to move away from that to a more efficient framework referred to as containerization. And in containerization systems, we replace the hypervisor with a container engine, and then all the applications run using a single operating system. So the container is essentially a more efficient form of virtualization. And so all of the trends in advanced communications that use virtualizations, not all, but the large portion, are moving to containerization. Okay, now when we look at communication, wireless communication standards, these standards come in what we refer to as releases. So right now we're kind of in the era of release 16, release 17, and the 3GPP. The release that's about to come on the scene is release 18. And what are these releases? They're basically just new updates. It's just an update nomenclature that is referred. Now, periodically, as these releases go up and up and up, rather than call it a new release, we eventually say, okay, we don't have a new release, we have a new standard. Okay, so if you're saying, well, what is 6G? in my prior analysis, 6G is about release 23. So when we get to about release 23, rather than say, release 23, eventually we'll say, okay, this is 6G, and then we'll start over again. Okay, so this is sort of how it works. Now, 5G advanced is really a point at which the 5G standard says we have most of the advanced capabilities of 5G at this point enabled in the standards. What are some of those advanced capabilities? Well, 5G is starting to integrate what's called non-terrestrial networks, meaning satellite communications, or which could be low Earth orbit, medium Earth orbit, or even higher altitude platform stations. 5G is integrating some energy efficiencies, precise locations, and is starting to leverage artificial intelligence. Now, 5G has not integrated all those things fully with a very robust enablement. That's going to be left to 6G, but 5G is sort of the bridge that'll start that process, and then 6G will look at many of these items as more native. So in 5G, we have, again, massive machine type communication, ultra reliable low latency communication, enhanced mobile broadband, and there also are low cost modes of 5G. One is referred to as reduced capacity or RedCap. Reduced capability or RedCap. And this capability is, let's say we have small sensors, maybe wearable sensors or sensors for let's say pollution monitoring or other things. So RedCap can operate in those modes. So what you see here are some of the use cases. And one of the things that the standards body has been doing, the 3GPP standards body, is defining different use cases that will be important for the public and for the service providers to enable, with the idea that certain use cases are very popular. And so the standard wants to sort of organize and orient its capabilities and its performance indicators around those specific capabilities. So you can see here what's called extensible reality or augmented reality mixed with virtual reality, UAV-based communication, vehicle-to-vehicle communication using a technology referred to as sidelink. There are enhancements in the what's called the SIM card. There's something called eSIM that is very popular. And again, non-terrestrial networks, cloud computing, and many different networking, flexible networking topologies. Okay, so what about 6G? Okay, so this is 5G. So think of 5G as a mobile version of the internet. So then what about 6G? Well, right now there are worldwide activities occurring in 6G. And one of the reasons that 5G is essentially extremely popular is because it's a worldwide standard. That is to say, there are very few standards that you can go from, North America to Africa to the Middle East to Europe and then to Asia, and still have essentially the same standard for communications. That is very unusual, and hence, if you have something in the standard and your equipment supports the standard, it can be bought by literally everyone on the planet. And that's why 5G is so incredibly important, because the standards are used across the globe. There are different explorations that are occurring in 6G all across the world. In some sense, there is somewhat of a competition for research and development talent, for IP in the form of patents, for university research, because everyone recognizes that as great as 5G is, 6G will usher in an even higher level of capability. Going through the standards is quite a involved discussion. So if you're interested in that, let me know. There's a group referred to as the International Telecommunication Union, and they publish different sort of visionary descriptions of what these future standards should be. And so the ITU has published some 6G standards for 2030 and beyond. And these capabilities migrate into a group called the IMT, and that migrates into the Wi-Fi and the 3GPP standard for cellular. Okay, so 6G performance. So let's look at what 6G performance is. So 5G performance looked at, capacity, latency, and like how many devices physically can you populate in a small regional area. 6G is taking those same parameters and expanding them. So it's looking at capacity, data rates, latency, reliability, battery life, and one of the key elements that 6G is recognizing is energy efficiency, and it's improving on things like security and resiliency, and as well as improving on latency. So you can see if you envision this inner circle as 5G, 6G is going to improve along all these different dimensions. What are some of the use cases? Well, machine learning, AI and machine learning is one of the key use cases for 6G. So when we look at 6G, AI and distributed cloud in communications, what's referred to as integrated sensing and communications, you can take different waveforms and you can actually use the waveform to communicate information. You could also use the waveform, specifically reflections, measured reflections of waveforms, to sense your environment. So if you want to create, let's say, a 3D sensed replica of the room you're in, you can send radar signals. If you want to detect, how close is the vehicle next to you, what the environment is around you, then you can sense that environment. And so here, when we're talking about sensing, it's typically in the term, in the framework of you can sense the topology, what's around you, almost as if it's vision sensing. That does not imply we don't have other sensors. So we can have, sensors that'll measure temperature, or sensors that'll measure, illumination and other things. But sensing in this context typically means a type of vision sensing. And so think of LiDAR, for instance, as a type of vision sensing. Energy efficiency, security. There's a lot of advanced multi-antenna capability referred to as MIMO, or multiple input, multiple output capability. And then spectrum. So 6G goes up into the terahertz range in terms of spectrum. So normally 5G, if I write this down, right? So 5G was typically between, let's say, 600 megahertz up to about 52 or so, let's say, gigahertz. Okay, whereas 6G is really going from 600 megahertz up to about 0.3 terahertz. Okay, so this is the typical range that's envisioned for 6G. So 6G is starting to go up into the terahertz range for communications, and in this range we can sense and do other things that you can't do at some of the lower frequency bands. Positioning, non-terrestrial networks, which we mentioned, but making these things native as opposed to operational. Disaggregation of the radio access network, and obviously higher data rates, higher speeds. All right, so if we look at 6G communication networks, you can see some of the examples. So what are some of the envisioned scenarios? Well, ultra high def video, three-dimensional video also. We had mentioned extensible reality, which is a combination of virtual reality, augmented reality. Some of you may have seen the recent announcement by Apple. They've recently put out a new augmented reality headset. It's very impressive from the actual reviews. We have mentioned for 5G enhanced mobile broadband, massive machine type communication, and very ultra reliable low latency communication. Well, 6G sort of expands on that, and so we have further enhanced mobile broadband. That is to say, a higher degree of mobility. Ultra massive machine type communications. That is to say, rather than 1 million devices in a kilometer squared, we're talking about hundreds of millions of devices in a kilometer squared area. A massive ultra reliable low latency communication with delays less than 0.1 milliseconds. Now, I've used this term latency, and the thing to think about with latency is you get tactileness with low latency, meaning I can flip a switch at one location, and because of the low latency, the system itself can control something at a remote location with such low latency that it's as if you're present at the remote location. And so this ability to control things remotely, whether it's a drone, whether it's a vehicle, whether it's a robot, it gives 6G incredible power to do things like perform remote robotic surgery. So I can be in San Francisco, you can be in New York, and I can perform surgery on you remotely. Now, obviously, it has to be reliable, and no one is saying that it wouldn't be better maybe just to sit right next to the person. But if your expert is in San Francisco and the surgery has to be done within this magic window of, let's say, 30 minutes in order for the patient to be saved, and then these kinds of operations can save many lives. So human-centric services, low power, extremely low power services, distributed artificial intelligence, including what's referred to as federated learning, where we use kind of a federation of learning systems and we combine those in an optimum way. A holographic video is another area for 6G. Space, air, ground, integrated networks. So these are all things that 6G is going to lead to, which ideally is this kind of utopian smart city of the future where everything can be done with, from your phone, from your computer. You can literally dial up, whatever service that you need to enable whatever capability that you want. Again, in terms of how much better 6G is than 5G, think of this outer ring as the 6G performance, and then this inner blob here that is a, I don't know, it's an 8-sided polygon of some sort is really the 5G performance. So you can see here the connection density is going to go up to 10 to the 7th. That's 10 million devices in a kilometer squared area. You can see that the spectral efficiencies will increase by a factor of 3, that the latencies will, I'm sorry, this is the data rate, that the data rate that you would experience will be a gigabit per second as opposed to 100 megabits per second. That's the average user, which is basically what you're getting typically if you're on Wi-Fi or if you're connected to Ethernet. And you can see mobility and latencies are all improved under 6G. Now, in my research lab at the University of Texas at San Antonio, one of the areas that I focus on is security. So UTSA is well known for security. So I've been with my students, we've been looking at integrating new waveform technologies, namely physical layer security natively into 6G. So one of the challenges is as you send more and more data over a network, there's a higher probability of incident of malicious behavior and of security threats and attacks. So what we've been looking at is, how can we take the communication network and make it sort of natively secure? And so the technology that we've been researching and we've published a number of papers on is referred to as physical layer security. And what we've been looking at is integrating that within a 6G environment and potentially using it as a next generation standard. What would that mean? That would mean when you turn on your phone, it's secure. When you send an information signal over your phone, it's secure. In other words, you really don't have to do anything. The phone, particularly the over-the-air waveforms, are secure natively by design, and hence it provides a certain level of security. Now, there are multiple layers in any communication network, and so if you secure the air interface, it doesn't mean you don't secure the computer networks that run behind the cellular network. You still need to secure those as well. So those would run in tandem with this. And you can see some of the extreme data rates. Automated intelligence, okay, is key for 6G. There are many different network topologies. One particular topology is referred to as a cell-free network topology, where we no longer have, let's say, hexagonal or octagonal cells, but instead we have irregularly shaped sort of regions, and the various radio access networks within the infrastructure communicate in a cooperative and coordinated way to enable what we call infrastructure-free capabilities. So this is one of the other areas, ultra reliability. And then finally, something called ORAN, which is Open Radio Access Network capability. This is really key because what this enables is a more, it enables a lot of the radio access network to run on commodity servers the way that your applications and your core network functions run on commodity servers. So I'll say more about that. So we have a vision also of a smart private campus. So, at the University of Texas at San Antonio, I've been working with a team to bring some of this technology to our campus. And so one of the things that we've been looking at are what's called shared spectrum combined with unlicensed spectrum. So the Federal Communications Commission has been busy at work opening up spectrum for cellular communications. And when I say opening up spectrum, what I mean is you can actually create your own private network. So let's say you have a small company. The company resides on, let's say, a 10-acre facility, and you need all of your associates to have phone service, but you're only worried about connectivity on your facility, your let's say 10-acre facility. So you can actually set up your own private 5G and in the future 6G network on a frequency band known as the Citizen Broadband Radio Service, or CBRS band. So right now the FCC has allocated approximately 145 megahertz from 3.55 gigahertz to 3.7 gigahertz carrier frequency. The FCC has allocated that band toward a shared spectrum model. So you could literally purchase a phone, you could put an eSIM in it or a physical SIM card in it and run on a CBRS band and set up your own network. So you basically would get a small 5G radio access network transmitter or transceiver, and you would download a 5G core services to your server, and you would connect a application server to that, and you could technically set up your own network with its own capability, as long as you run on this band. So the FCC is busy opening up other bands as well, but this is one of the key capabilities. There's other technology in the future that's envisioned. One is referred to as reconfigurable intelligent surfaces. So that's what you see here, where you actually plaster on walls specific surfaces that can reflect in a controlled way signals, and that can aid in certain signaling modes. And then we think that, or at least my vision of a killer application in 6G is 6G connected autonomous systems or autonomous vehicles, where essentially vehicles, they drive themselves, but they can also be driven from the network. Okay, so you can actually take, let's say you have a small company, a small trucking company. You can reserve a facility where all of your drivers go to that facility and drive trucks remotely. So rather than getting in the truck and physically being with it as it's driven, instead you go to a remote facility and drive things remotely over networks like 5G and 6G. So that's a technology of the future. And then an extension of that is, rather than having a person drive a vehicle, you could actually have an intelligent, artificial intelligent agent, a software agent, remotely driving vehicles over wireless communication links. And you may say, why do that? Because you can put a big brain in a remote data center and a remote edge service that maybe wouldn't fit in a vehicle. Okay, so if you do these things remotely, you can enable extremely powerful AI systems to drive your vehicles. And that's what you want. You want intelligence that's able to know the weather, the forecast, the traffic, can see around corners, can communicate with other vehicles, and can stop on a dime, account for anomalies, and that can be done. So I talked about this concept of ORAN. So ORAN is Open Radio Access Network. Basically, it's a standard for this system that used to be called a base station. Well, now these quote unquote base stations have been broken up so that not all the communication services have to be physically in the same system. They can be broken up into a distribute unit, a radio unit, and a centralized unit. And I haven't mentioned this, but 5G also separates control from the user plane. It separates what's called the control plane from the user plane. But this system here is essentially this system here. Now, in addition, ORAN has created some standards referred to as non-real-time intelligent control and near real-time RAN intelligent control. And so these systems allow us to do things like, we could put in the near real-time intelligent control system an ability to detect spectrum, an ability to detect other users. Maybe it's detecting interference or jamming. And so a lot of that spectrum agility can be written in a language referred to as XApps. So if you see this term XApps, this is really a term for the application of software to perform control for a near real-time radio access network intelligent controller that would control how the radio units, the distribute units, and the centralized units interact with the spectral environment that they are in. Okay, so I've mentioned that ORAN can be disaggregated. So that's one of the key things. So now, why would you want to disaggregate a radio access network? Well, it's because, maybe you want to put a really low power radio unit on, let's say, an aerial system, or maybe you are in a remote area, and so you need just a really low power remote site And so you can take a portion of the genome B, put it in that remote site, and then disaggregate it and put the other portions close to systems where maybe there's power or cover. Okay, so real-time intelligent surfaces. This is referred to as RIS, and real-time or reconfigurable intelligent surfaces are a emerging technology, and the thing to keep in mind about this is the following. Communications historically has not had to be line of sight. Communications historically, particularly in the bands that we normally operate in, doesn't require that the transmitter have a direct view of the receiver. It just sends the signal in a kind of omnidirectional or slightly directional pathway, and the signal arrives. As we move to higher frequency bands, however, it turns out that signaling necessarily in a native sense becomes more directional as you go to higher frequency bands. So if 6 gigahertz, I'm sorry, if 6G is in the terahertz range between 0.1 and 0.3 terahertz, then that signal is not omnidirectional, it's more directional. And one way we can enable broad coverage in these higher frequency ranges is through an augmented technology referred to as reconfigurable intelligent surfaces. And so this is a paper by Poulakis that you can find. It talks about 6G metamaterials solutions. This was published in 2022. So a reconfigurable intelligent surfaces comprises an array of unit cells. In each cell, there's a metamaterial that alters the phase of the incoming radio wave. And the resulting wave interferes with other waves in a way that allows the reflection to be controlled. So you can actually direct, because can you see this one? You can actually direct the reflection of these surfaces using a microcontroller based system. So in a nutshell, this new technology will enable low-cost, high-frequency communications. Non-terrestrial networks. Now, what is this about? Well, in non-terrestrial networks, we have a large number of configurations that allow, different orbit constellations and beamforming strategies. But generally speaking, if we have a constellation of satellites in space, we can cover vast quantities of area in North America, but also around the world. So this gets to the ability to communicate kind of anywhere, everywhere. And in addition to satellites, and typically most groups are looking at what's referred to as low Earth orbit satellites. But you could also look at high altitude platform stations, which my graduate students and I are looking at as a height, where these are about 20 kilometers, whereas low Earth orbit, if I go to the next slide, is between 500 and 2,000 kilometers. So these are the different orbits that you can pursue, and you can also have geostationary orbit. The challenge, though, is as you move the satellite further into the atmosphere or further into space, away from the planet, you may get larger coverage, but you get longer delay. Okay, so that delay, which you can think of as a delta in time, can sometimes be exorbitant. And it's not just the propagation delay, it's also the computational delay to process the signal in deep space orbit. There are standards that the 3GPP is developing in non-terrestrial networks. This is expected to be native in 6G. That this is your phone, when it's a 6G phone, will be able to communicate directly to satellites. Now, how does that happen? Well, if you look here, this is a diagram of how that would happen. So you would have a data network, a core network, an edge network, and then we have our radio access network. Now, I've already mentioned that these radio access networks can be disaggregated into multiple pieces, so you can place them at different locations depending on, whether you need cover, whether you need power, whether you have power, whether you want a lightweight, low power element at some remote location. For it to communicate with satellite, then this Geno B needs to communicate through a gateway system to a satellite. And the satellite is expected to communicate directly with the UE, right? So this is a model of an end-to-end 6G non-terrestrial network system. We can also, if we take that system, we can also enable communication on unmanned aerial vehicles. So you can imagine if we start with a space-based system, something like this, that rather than have it communicate all the way to the mobile, we could have a more of a tree-based communication link where the satellites communicate with unmanned aerial vehicles that may be at some height in the air, and these systems can communicate with each other. They can also communicate with ground systems, whether they're vehicles, whether they are phones or buildings that are connected to the network. So 6G is also moving in the direction of aerial systems, which think of it as non-terrestrial, and the non-terrestrial could be a height of 200 meters for an aerial wing vehicle, or it could be 20 kilometers for a high altitude platform station, or it could be low Earth orbit or other satellite constellation. Now, in terms of killer apps, one of the apps that we had looked at that I've been thinking is a very what I call should be a very popular capability is autonomous driving control. Okay, so in the previous example I gave with that, you could have a trucking company capable of distributing using automated agents distributing trucks across the country with supplies. So if you need logistics and you are managing an Amazon warehouse, you program your distributed network of autonomous trucks. You have your loaders and unloaders, obviously, which will involve robotic loading and unloading. And you can start to see you can have an end-to-end system where literally from one warehouse to either a factory floor or another warehouse, you can have individual items literally shipped across the country without requiring sort of human intervention in that sense. Now, short of that, we can also ship people, right? So in the future, a car is valuable, but imagine you can jump in the back seat of your car, program your car where to go, and then you can get all your work done while the car is driving, right? So that's sort of the vision. And in order to enable that, part of the thesis in my research lab is that you need 6G, vehicle to network communication, because once the network can control the vehicle, you basically have increased by, orders of magnitude, the intelligence and the computing that vehicle can get access to. So the vehicle sensors can be sent back on a communication network to the network. That network can then use certain learning algorithms and learn information about the vehicle, the traffic, the weather, the roads, and the aggregation of all that information in the network will give unprecedented control and an ability to move traffic, physical vehicle traffic, very, very rapidly. So we haven't said a lot about AI. So AI is for sure a emergent and extremely important technology, and it's equally important in communications. Now you may say, well, what are we going to use it for? Well, historically, we've used a lot of linear optimization algorithms in communications when we're trying to optimize the network behavior. But a lot of that can be programmed into a machine learning algorithm, which can take into account all sorts of linear effects and interactions, including, estimators for the channel, information about the spectrum usage, policy information, throughput, energy, costs, it can essentially enable someone who is not necessarily an expert to use these expert agents, these intelligent agents, to optimize and run networks so that you don't have to be an expert all of a sudden to run the network. You simply need to get access to the automated experts. Okay, we're running out of time. So 6G connected automated vehicles is an area that I'm very interested in. These are some of the publications that we have pursued on that. I did also publish a, publish a document with the what's called the Day One project on integrated automated vehicles with 5G networks to realize the future of transportation. So you may find that interesting. So in conclusion, 5G 6G is not your grandfather's communication system. Okay, so these systems are cutting edge. They convergent. They integrate the most fantastic technology in networking, in cloud computing, in computing itself, as well as wireless communications. I do offer training and education courses in 5G. So if you do find that your organization needs that, it's possible I may be able to offer that as a to your organization. And also, I am seeking collaborators for an advisory board on a smart private 5G 6G campus at UTSA. So I've left my email address here. So please get in contact with me if you have questions. And I hope I've been able to convince you of the really the fantastic advances in 5G and 6G. So with that, I'll stop and see if there are any questions.
All right, thank you. Okay. I didn't see anything in the chat or reaction. So any question, please open up your audio link. So I wonder, do we have enough spectrum to support all those 6G?
Yeah, great. That's a terrific question. So do we have enough spectrum? So it turns out that if we use exactly the same spectrum that we're using today, then the spectrum is very limited. So what's being done is two dimensions are being used. One, we're going to higher carrier frequencies. So we're moving into what's called the millimeter wave band. So we're operating at 28 gigahertz, 39 gigahertz, at 70 gigahertz, and for 6G, we're going even higher into the terahertz range. Now, as we move to these higher bands, higher carrier frequencies, there is more bandwidth available. In addition, the other dimension is antennas. So there's a lot of work on what's called the use of massive numbers of antennas. And it turns out that if you expand the number of antennas in the same band, you can send significantly more data, more throughput. So those are the directions that the field is going into to expand the amount of data.
So one question is if you run it at 6G, you run at very high frequency, like you said, 1.3 terahertz.
Yes.
The distance that travel, the signal travel will be much shorter, right? So you need more antennas or more relay.
Yeah. Okay, so it's a good point. So the idea is, again, as you move to these higher frequencies, the actual propagation distances at these higher frequencies is lower. And hence, how do you compensate for that? So one way to compensate for that is the systems themselves, you can fit more antennas in the same space. So, whereas, let's say a millimeter wave, we may have had 200 antennas, as we go to these higher sub-terahertz bands, we can fit thousands of antennas on a board, on a microchip. And so by coordinating the antenna transmission, now there are many different modes of MIMO that you can use, and many different modes of beamforming that can be used. So these different sort of what I call smart antenna modes can use many more antennas to add some level of coherent gain to help recover that path loss gain.
Right. Dr. Kelly, is it possible to get a copy of your slides?
Yes, so I'm going to send out a copy of the slides, and so I will be giving those to Kai, and we'll make those successful.
Yeah, so I will publish that in our website, and also this recording will be available probably in 1 week, so we can look at a recording also.
Thank you.
Okay.
Yes, that sounds good. And again, if you have any follow-up questions, please, I would encourage you to email me. I've been studying these technologies very in some depth for 6 years now, and hence there's a lot there. And one of the things I'm just going to say is this. This kind of presentation, in some sense, I really enjoy giving it, but in the other vein, it's not really possible to share like 5G, 6G technology in a short session like this. And so if you are interested in the field, you kind of need to take a course. I think it's even beyond the realm of like reading a single book to try to understand the technology. There's too much of it right now. And so if you are interested in it, I would really encourage you to, seek a course at a university. I teach some courses on that. Obviously, I would encourage you to take my course, but that for sure is what I would recommend. Or you can look on places like Coursera and other places.
Yes. So just one notion that just kind of look at the email address again. The last name is Kelley. So a lot of time I made mistake. Just put that Kelly.
Okay. Yes. Anyway, yeah.
Right.
So and what I would say too is you can look me up at the UTSA website. So if you're having trouble finding me, just look me up on the web at UTSA, and you can connect with me that way.
All right.
Okay.
So any other questions from the audience? Well, if not, then we'll see you next month, the third Thursday evening. I'd like to thank Brian for Spec Talk.
Thank you.
All right. So with a lot of possibility for us, also job opportunity for the younger people in the group. And all right. So thank you. Have a good evening, and thank you again, Brian. See you later.
Bye-bye.
Thank you. Thank you.
Bye-bye.
Thanks, guy. Thanks, Kelly.
People join. So I've been working in this 5G and 6G area now since about, well, I started studying it with my graduate student about 2016 or so, 2016 approximately, is when we started really getting deep into 5G. And then I joined there was an effort announced by the Department of Defense on 5G, where the Department of Defense wanted to develop 5G experimental sites. And so this occurred after I gave a talk. I gave a talk in about 2019
Right.
to DOD.
Mhm.
And, apparently it resonated with them. And I ended up traveling up to the Pentagon and speaking with some of the folks there. And they were about to release a effort at DOD to develop 5G networks. And they referred to it kind of, sort of an inside term called the tranche sites. I don't know why they use that term, but these tranche sites really spurred the development of 5G within the Department of Defense. And so you can see on the, in the current research efforts, one of the things that I cited was I was named the principal investigator in 5G core capability and security, and in another program called 5G telemedicine and medical training for the Joint Base San Antonio site that was funded by the Department of Defense. So, so we embarked on setting up a team, developing a research proposal. We had industry days, and essentially what we were doing is we were soliciting for partners to work with us to design a very advanced 5G capability, but it was end-to-end. So it wasn't just like a 5G experiment or some 5G simulation. It was actually like an end-to-end 5G network, similar to the networks that the operators, the AT&Ts, the Verizons developed, except on a much smaller scale. And so that started in 2020 is when it started. So I was with that effort for about 2.5 years till about till recently, till about end of 2022. And then joined another group in the Department of Defense within the Office of the Undersecretary on what's called advanced research. So right now, I've got a research contract through the university with the Department of Defense to work with them and other research teams on advanced sort of what they call future G networks, and these are sort of beyond 5G capability. So I've been doing that now for about the last 3 to 4 months is when I've been working on that. So whereas my old role was centered at Joint Base San Antonio, my new role is sort of across the country.
Oh, okay.
So I've got research teams across the country that I'm working with. So the goal is the same. So one of the things, and I'll discuss this a little bit more at 6 when more people join, but one of the things that the Department of Defense and the US government discovered is you can do a heck of a lot with 5G networks, 5G communications. And when I say a heck of a lot, what I mean is essentially it can cover about any kind of application, any style of communication you want. It can behave as a traditional computer network. It can behave as a wireless local area network, similar to Wi-Fi. It can behave as a wide area network for cellular. It can connect to satellites. It can have really high data rates or low rates. It can operate at bands all the way from 600 megahertz all the way up to 70 gigahertz. and technically 52, but you know, so it has a tremendous flexibility. And for that reason, if you look in the like in the presidential memorandums and presidential statements, the whole U.S. government has really come on board with 5G technology, and so they're very interested in developing that technology for DoD, but also for other entities, Department of Energy, Department of Commerce, the National Institutes for Standards. All of them are really focused on 5G technology, and I'll try to explain exactly why that is in a little bit more detail in just a minute. But I from that effort, from my academic efforts in studying 5G, I have picked up tremendous expertise in this specific area, and really, when I say 5G, there's a transition that occurs when you move from 5G to next generation 5G. And it sort of goes in steps that are called releases. And then those steps eventually turn into a new version of G, which in our case would be 6G. So within the academic research labs across the country, a lot of researchers are looking at, what should 6G be? What kind of technology should it involve? And it's really the core basis of 6G is really 5G. So when I talk about 6G, I recognize that, no one has a 6G phone, no one has 6G networks deployed, but the research has to really precede the deployment by some good period of time. Typically, whenever you see something on your phone, it would have been, developed in research labs about 7 years prior. So most of the stuff that ends up in your phone, 7 years before that, some researcher in a lab was prototyping it, right? And that's sort of the lag time that you need before you see it, because when the operators actually deploy something, they need to make sure it works. I mean, everyone's got a phone, and I just bought this i14 Pro actually, which is a great phone. But when you buy these phones, everyone expects them to work, and so that means that all the bugs, the kinks, the software, the development, the networks, everything has been well tested. So with that, let me just pause, and Kai, I don't know if you want to begin.